Our last but not least, we have our speaker. Oh, wait, slide. Our next speaker is Rafal Szarecki from Juniper, and he's going to speak about laws in FatTree forest and route out. Thank you.
Thank you. Hello. Okay, I'm lost between you and gear or beer, depending what you like, so don't be lost in the forest. What I would talk about the specific problem and solution for the data center fabric, and routing in that. So we go through the very quick overview of the routing, what is the routing today, technology we have, and why the DC fabric is quite specific problem for the routing. And then finally, I give you a quick ride on the Rift, which is just new, I would say new concept or new protocol, new algorithm even for the closed networks and FatTree networks. So we have generally, excuse me, I will try to keep closer to mic. We have generally two kind of routing protocols today. One is the link state, and we use the shortest path first or Dijkstra to to resolve the problem, the graph problem. And the other is path or distance vector protocols. With the first one, the principle is that every node describes themselves and his close proximity, so his links and neighbors, and send this information to everybody else. We call it fluid. So every node in the network has exactly the same data set and use the Dijkstra algorithm to find the best path to the prefixes, which is one of the node attributes. That algorithm is pretty fast and pretty common used. OSPF use it, ISIS use it, the old one with gray hair, remember maybe PNNI, Trill, routed bridges. It's quite fast and when it converges, but has some scaling limitation. The other protocol is a path vector or distance vector, and here, actually, every node sees only what is reachable through his neighbor. And when the destination, so the prefix information traverses the network, it gain or gather the metric. The metric could be a value, it could be an AS path, the elements, the length of the AS path. So the selection and computation of on every node is executed on different data set and is very local. These protocols very well works with when we need the policy routing, when we need the control routing. It scales very well because it naturally allows for aggregation on every hop. However, it's not that fast. And it's built into the protocol, into the algorithm. You can see that the link state distribute the same data set across the network, and then the computation is kind of running in parallel with the shift of the network latency, while the distance vector is like a one-hop transmission, computation, transmission, computation, so it chain it. However, they share one very fundamental attribute. All the existing algorithms are designed to work in any topology. You can run whatever connection, and the ISIS solves the problem, or your BGP properly configured find the path. Data center fabric, or closed network, or FatTree networks, more specifically FatTree networks, are quite specific in his topology. So we not necessarily should use, or if we have a specific problem, we may find a better solution specific to the problem. We not have to use the super glue for everything if we want to tie together, let's say, glass. There are specialized glass glues. So what is the closed? Sometimes we call this closed topology. What is really, it's a FatTree because closed assume the same number of switches on every layer. In data center, usually we have more tors than spines. But the fundamentals are the same. It's a very densely connected network. The principles was developed in the 50s for these TDM switches. And yeah, today we call it a folded tree or folded close because switches are bidirectional and we close the loop on every stage. Anyway, to solve the problem of the graph, to find the routing through this type of topology, which is very densely connected, very hierarchical, very symmetrical and organized, we either use the BGP, which is the common practice, and then we need some Bandaids, right? We relax ECMP rules, we have add path for multi-homing, we allow the ECMP over between different ASs. For auto-provisioning, there is a lot of proprietary extensions, either based on LLDP or some specific vendor or even user or operator procedures. There are also cases where we know where the traditional IGP is used. Both of them have some limitations. And my colleague, Tony, did some analysis. What we really would like to have in such well-defined close network where we know exactly the topology. And there is a list of capabilities and how we rate it against the existing implementation over the path vector protocols, or BGP if you like, be more specific, or the link state. But it goes down to fact that, hey, because we exactly know what is the topology and what is the hierarchy, why my protocol, when they try to build the graph and build the adjacency, not ensure that there is no violation? Do I need all information, like in a link state, available on any stage? Maybe it will be nice to dump down the amount of information and states needed at the bottom level, on the top of the rack level, to something really minimal. We don't want to spend money there, right? Even I'm from Juniper, so please. This comes to the automatic disaggregation. If we aggregate the information, what distance vector actually allows, but during the failure, we still want to keep the connectivity without the losses, so we don't want to send the traffic to some black holes. And finally, we don't want because we have very dense network, we have a lot of connections, right? There is a lot of links which may change the states because of the failure. We don't want to chase the whole data center just because of the single link. So some level of localization would be nice to have. And again, we don't have it. So that's the principle of the rift. We try to address it. On one side, the rift, routing in the FatTree, that's why it's rift. It takes the best from the well-known link state and distance vector. So converge as fast as the link state, allows the automatic detection of topology, which is new actually, minimize routes and states on the top of the rack switches like a distance vector, allows for high level of ECMP, converge fast, but reduce the flooding. In a very dense network like a Clos, the flooding and reflooding is high of expense. There is a lot of redundant information. It's taken out. And finally, Rift allows for the things which are generally not supported by current protocols, like automatic disaggregation on failure, or minimize blast radius in case of failure. Finally, the carrying the opaque value, so key value. We don't know for what reason yet, but the part of the protocol is to allow carry different information. With that, let's look how it works. What is the proposal? Fundamentally, it's a hybrid. So the information, routing information traveling from the bottom to the top is like a link state protocol. So every node describes themselves, their network, their links, their adjective prefixes, and flood it to the top. On the picture, the spine layer, which is green one, for the bottom to top or south to north, it just flood the update without changing, like in ISIS. However, in opposite direction, the routing information is generated on node, send it to the adjacent node down, which consume it, sync it, and then the new information is created, the new update is created and sent further down. And you can also notice here that in normal situation, in the simplest possible case, we need only default. Finally, there is one extra strange capability. It's a bouncing. So the information sent from the node down is bounced back to the level up. And this one is used for equal connectivity group detection, which I will describe later. And this is a foundation for the automatic disaggregation and flood reduction. So we start from adjacency information. There is an element, call it a link information element. You can think about it as like a hello. And there are three fundamental information about the node. It's a node ID, which is unique. You can, it's 64 bits value, but just think it's as a unique value. And two numbers, the level and the pod ID, pod number. Interestingly, the level 0 means that this is a Tor. And assumption is that this would be a factory default. So when you get the switch, you can connect it as a Tor and it's ready to go. The other, the pod ID, it's also an interesting one because, yes, you should configure it, assuming that you have multiple pods in the data center. However, pod 0 means that it's any pod. And the actual pod used during the further procedure is inherited from first adjacency formed. So this way we can we not have to specify the pod during the installation. We just install the box, and from the first northbound neighbor, the pod ID will be inherited. What it means? It means that if we have the illegal connection, which breaks the FatTree topology or closed topology, if you like, the adjacency will be not formed. If we have the connection from 1A to 1B by miscabling, there will be no adjacency formed because it's different pod. Same if we have connection from the C0 to B0, right? This cabling could be there, but the connection will not happen just because the difference in levels is 2, and it's not allowed. So this way we enforce the topology. And then there is a flooding of the topology information elements. And there is many of them defined. We will focus on 2 of them, the node tie and prefix tie. And there are different procedure, as I said, depending which direction information is flowing. So here, node ID define the topology. Nodes, links, neighbors, but not IP prefixes. And when it travels from south to north, it's just to build a topology database. So effectively, the top spine has the full view on all connections, top spines. But the lower level spines, or Tors, has no visibility to topology. Tor has just see his neighbors because he not get this information from the rest of the network. In the south direction, the node information are used, of course, to discover the who is my neighbor, and also is used to bounce it back. And bouncing back will be described in a minute. Prefixes are quite easy to understand. Prefix, the tie is just like IP reachability, TLV in ISIS. It's just information about the prefix. So how the routing looks in the steady state? We start from the simple case. our middle layer spine advertise themselves to his neighbors with the prefix 0, and that's it. From the leaf perspective, that's enough to send the traffic to any destination. And the top layer spines are doing exactly the same in the south direction. So far, so good. By the way, we have aggregation built in. On the opposite direction, every node is sending his tie, so his description, in the flooding fashion. So all nodes on the north, on the top from the originator, has the full topology information. Some interesting capabilities. Leaf has only default root. So you not need much of control plane power there. Spines in the pod 1 has only information about prefixes in the pod 1 and default to the higher layer spines. Similarly, spines in pod 2. And only spines at the very top level has the full visibility to all prefixes and full topology. We have localization of the routing information, which helps in the localization of the churn if there is a link failures, and we have aggregation. However, what happens if we have a failure? We use defaults, so we potentially can send the traffic somewhere where there is no, where the traffic will be dropped. And now the concept of the equal connectivity group comes. So spines has the capability to detect which other spine has the same neighbor set. And this is done by, this happens by disbouncing, right? The spine 31 send the information south tie with the neighbors, 111 and 121. And and the neighbor 111, as on the picture, bounce it back to spine 32. So spine 32 can say, hey, my neighbors is the same as the neighbors of the spine 31, and we are on the same level. So we are equally connected. You can read it later. How it can become useful? Because now, if the connection between spine 31 and the spine 211 breaks, spine 32 can detect this fact. We'll see that, well, the spine 31, which is in my equal connectivity group, now has no neighbor 211. Therefore, spine 32 will send additional prefix tie with the destination C and D, which makes the spine 111 learn that these specific destinations, C and D, are reachable only through spine 32. So there is no black hole. And still, the top of the rack switches on the, that's your left side, yeah. On the left side, can live with the default only. There are a couple of other capabilities, right? Traffic engineering is possible by inserting prefixes or policy-guided, not prefixes, by inserting policy-guided prefixes. Packet format here is purely model-driven, and it's channel agnostic. Yes, it could be UDP. We can also use TCP. We can use QUIC. The protocol is not tied to any transport. UDP is probably the easiest to implement. Purging is not part here. The experience with the ISIS shows that or OSPF shows that the purging is complete, is very, it's not really useful. Where is the status of that? It's individual contribution to IETF working group. right? So the work was started. It was presented on the last IETF. So the work toward the special routing protocol or procedure for the FatTree and the fabric starts. From the implementation perspective, the prototype code exists. So we run some proof of concept validation. We collect the performance data. In general, we can say that the Rift converge in the half-time of the ISIS. That's general guidance, and requires half of the resources on the spine node. The interesting is the top of the rack version, because when you look closer, top of the rack never gets fluid. It only receives the south thigh. Effectively, there is no need to run the extra on the TOR. So the implementation of the TOR could be significantly simplified. And of course, there is a call for action, right? You can join the IETF working group. You are welcome to share opinion, mostly with the author of the draft, but I can be a proxy. And finally, the data structures for all the packets are documented in the draft, in its individual draft. I will show you in a minute how to find it. So because the data structure are defined in the Google protobuffer format in the draft, so you can just take it, compile it, and you have at least the data model for the all communication available. So I promised to show you draft, which is the first slide. So let me move it. Yep. My Polish colleague, so I'll give you a few minutes to write down the surname. That's all I have to plan it to tell today. If you have any question, I'm open and happy to hear.
Yeah, Ashley Hatch with Facebook. Besides having the complete failure model between nodes and the spines and leaves, is there any consideration for an equal cost multipath information propagation to inform lower devices in the hierarchy of to send traffic in an unequal way to mitigate, for example, one of the ones you mentioned, you could send 66% to one because it had 2 links. You could send 33% to another because it only had 1 link, and manage that.
So there is a way to do that. There is a policy-guided prefix topology information database, so we can propagate this kind of information. The work is in progress, so it's a kind of next stage. But it's a part of the. We have a mechanism. We don't have a really full-blown prototype for that.
Okay, thank you.
Hi. Hello, Christina Chu, NTT. You talk about, you tested this and you collected some performance data. Can you comment on the performance data that you collected?
Yes. So, well, we tested in it's a piece of software at the moment. So the testing was done in a virtual environment, even not virtual Junos. It was just running multiple virtual instances, like containers of this process. And on the same hardware, we have the same model for the general link state database, right? So running at exactly the same hardware, at exactly the same number of nodes, exactly the same topology, cut the convergence time in half. Of course, I cannot say it was 30 milliseconds or 200 milliseconds because it depends on the on the platform and on the, but the ratio is there.
Okay. Thank you.
Okay, I think that means that there is a beer time.